Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this video I'm going to talk about how to use control variables in regressions. We're also going to learn about how to handle categorical data in a regression because control variables are often also categorical variables. Let's return to our Mincer equation, which is wage equals beta naught plus beta 1 education plus epsilon. In the last video, we talked about the problems with running this regression. There are potentially many omitted variables hiding out inside of our error term that are also correlated with education. We talked about ability last time, but there could be more. The first strategy we're going to talk about for dealing with this problem is to use control variables. Control variables are variables that, had we left them out, they would become omitted variables and cause problems, and so we are including them in the regression to prevent that. Control variables don't have to be causally interesting to us at all. We might not care about the relationship between a control variable and the dependent variable. It's just there to help us establish causality for the variable we do care about, in this case, education. Generally, the only reason that they're in there is to cut down on endogeneity problems. When coming up with a regression model, the first thing that we want to do is brainstorm some ideas of variables that might be correlated with both our dependent variable and our explanatory variable of interest. We've already talked about ability, but another possibility would be experience. Let's think about how we might sign the bias for experience. First of all, what's the relationship between education and experience? People who go to college and complete more education generally have a little bit less work experience than people who went straight to the labor force after high school. That means that there is a negative correlation between education and experience. Experience is generally positively correlated with wage because the more work experience you have, the higher your wage is going to be. This is going to make our overall bias negative, meaning that we are going to underestimate the effect of education. People who are more educated have less experience on average. This will make it look like education is less effective than it really is in increasing wage. Back over here in Excel, we have a sample that we are going to use to estimate our Mincer equation. Let's start out by running our baseline simple regression. So we're going to go to Data Analysis, choose Regression. For our first regression, we are simply going to regress wage on education. We'll select Labels. Let's take a look at these results. In this data set, education again is in years of completed education, and wage is the monthly wage. This tells us that for every year of education, our workers will earn about $60 more each month. However, remember that by leaving experience out of our regression, we are ending up with what we think is going to be a negative bias. That is that we are underestimating the effect of education. That means that this $60 might be too low. Let's go back to our data. We're going to run a new regression where we will include years of experience in the regression. We'll keep the Y range the same, but for the X range, we're going to select education and experience and run our new regression. Let's take a look. First of all, we have a positive coefficient for experience, which lines up with what we predicted. People with more work experience get higher wages. But the more interesting thing that's happening here is the coefficient estimate for education increased. This lines up with our conjecture that we were underestimating the effect before. By adding experience into the equation, what we get is the negative bias removed from our estimate. When we remove a negative bias, the estimate is going to go up, which is exactly what we see here. Now we estimate that each year of education, holding experience constant, will get us $76 more wage. So far in our regressions, over the last several videos, we've dealt strictly with numerical data. These are things like wages, prices, and output that can be measured as numbers. However, many useful controls that we might be interested in using in a regression are categorical variables, not numerical ones. This includes things like state of residence, marital status, sex, or race, which can't be quantified. There is no way to include categorical data directly in a regression. We're going to have to do a little bit more work. What we need to do is convert our categorical variables into dummy variables. Dummy variables have a few other names, such as indicator variables, or just dummies, which is probably what I'm going to refer to them most often as. Dummy variables have a value of either 0 or 1, which we can think of as off and on. A dummy variable will tell us, does this specific observation within our sample fit into a category, or does it not fit into a category? For example, let's say we have a dummy variable that is employed. The variable employed would be a 0 if not employed, so if you don't have a job, you have a 0, and a 1 if you are employed. An important thing to remember when creating dummy variables in your dataset is that we always want to select a base group. For our example, if we're thinking about whether somebody is employed or not, we want to think about either not employed or employed as our base group. For the other group, we have a dummy variable. In our example here, not employed is the base group, so we make a variable for employed. If you wanted to, you could instead make a variable called not employed that is reversed. 1 if not employed, and 0 if employed. Now we've selected employed as the base group and not employed has a dummy. Mathematically, it does not matter which one you pick. The interpretation once we run the regression will be a little bit different, but either way is completely fine. What you do not want to do is make both an employed and not employed variable and have those just be the reverse of each other and include both in the regression. We cannot do that. Doing that makes it impossible to run the regression. This is a simple example where we only have two possible states, employed or not employed, but we might have categorical data that has many different possibilities. For example, suppose we had in our dataset people who live in all 50 states. We would select one of those states to be our base group, and then we would create 49 dummy variables, one for each of the remaining states. To illustrate this, we're going to look at a new dataset called SD Categoricals. This dataset comes from the 2017 American Community Survey and is entirely from the state of South Dakota. We have several variables here, some of which are numerical. So we have wage, typical hours worked in a week, and age. Those are all numerical variables. We also have a few categorical variables. Sex, so male or female. Marital status, that has several different options. And then employment, employed or unemployed. Let's suppose we're interested in estimating the wage gap between men and women. In order to use the sex variable in regressions, we are going to need to create some dummy variables. I'm going to create both options. First, I'm going to create a female variable. To create the dummy variable, we need to use the formula if. The first argument of if is the logical test we're going to do. So we're going to select the cell here that says male, and we'll put in equals, in quotation marks, female. 1 if it's true, 0 if it's not true. For our first observation, we had a male, so we get 0. I'm going to copy this down. And what we see is that for the second one, we have female, and so we get a 1 there. That is how we create a dummy variable. I'm going to go ahead and make one for male as well. So I'm going to do equals if, select the cell, equals, in quotes, male. Whenever we have a variable that is words, we have to use the quotation marks. If it were just a number, we wouldn't have to do that. 1 if it's true, 0 otherwise. I'm going to copy this all the way down, and what we see here is that the male variable is a 1 whenever the female variable is a 0. The first regression that I'm going to run will have wage as our y variable, And for our X variable, I'm going to select female. This means I have selected male as the base group. The results show that we have an intercept of about $40,000 and then a coefficient on female of about negative $10,000. This means that the average wage for men is about $40,000, and when we add female in, that's going to subtract about $10,000. Going back to the data set, I'm now going to run a second regression where instead of female as the X, I'm going to choose male. Running this regression, we have an intercept of about 30,000 and then a male coefficient of about 10,000. This is the opposite of what we got before. Now, female is the base group, and so the average female wage is 30,000, and when we add male to that, we get an additional 10,000. So we end up at the exact same place, it's just the interpretation has flipped. I'm going to write out these equations to illustrate this. For our first regression, we had wage hat equals beta naught hat, which was about 40,000, plus beta 1 hat female. For our second regression, we had wage hat equals beta naught hat plus beta 1 hat male. In the first regression, for men, female equals 0, so this whole thing drops out, and so we predict, on average, men get beta naught hat in wage, which was about 40,000. For women, the female variable becomes 1, and so now the predicted wage for women is beta naught hat plus beta 1 hat. And beta 1 hat was negative, so we would subtract from the prediction. In our second equation, female was the base group. So for women, male would be 0, dropping this whole thing out, and we would predict their wage at beta naught hat. That was about 30,000. But for men, now the male variable is 1, and so we would predict beta naught hat plus beta 1 hat as their wage. In this regression, beta 1 hat is positive, so we would add to that for the higher prediction. It does not matter which one we pick, we just need to choose 1 as the base group and 1 to get the dummy. For the purposes of this video, I'm going to choose male as the base group and have a dummy variable for female. We now ask the question, is beta 1 hat a good estimate for the wage gap? We need to think about whether or not there are omitted variables. Is being female or male correlated with some other variables that are also correlated with wage? If so, we're likely going to have a biased estimate. Let's think about some control variables we could add here. The first variable I'm going to try adding will be age. Let's run a new regression. We'll keep the Y range as wage, but we will add for the X range age and female. Taking a look at these results, we have an unsurprising positive estimate for age. People who are older tend to make more money. But let's compare our female coefficient here of negative 10,600 with the original one we got, which was about negative 10,700. This is almost exactly the same. It's only about $170 apart. This tells us there is relatively little correlation between age and female. Men and women are on average about the same age, which makes sense. While it's true that women tend to live longer, we are just looking at men and women in the labor force, and there doesn't tend to be much of a difference in ages there. Therefore, age was not doing a whole lot for us here as a control. It might be interesting, but it's not really removing much bias. Let's add another variable. I'm now going to add the variable for whether or not a person completed college. Unsurprisingly, we get a large positive coefficient on college. Completing college is going to have a large increase in wage. What we notice about the wage gap, though, is that it has gotten even more negative than it was before. This means we removed a positive bias. Why might this be? To sign the bias, we need to look at the relationship between college and wage first. That's positive, as we estimated. But what is the relationship between college and female? As it turns out, women are more likely to complete a 4-year college degree than men. That gives us a positive relationship. With both of these relationships positive, a positive times a positive will give us a positive bias. We need to think about both of those relationships to understand the sign of the bias. Since we removed a positive bias, our estimate went down, or in this case became more negative than it was before. Let's go back to the dataset and do one last regression. I'm now going to add typical hours to our regression. Unsurprisingly, people who work more hours tend to have higher pay. But what's happened to our wage gap estimate is that it's smaller in absolute value, or less negative in this case. So that means we've removed a negative bias this time. We've already established that hours has a positive relationship with wage, but what's the relationship between hours and female? On average, women tend to work fewer hours than men. This could possibly be because of taking care of childcare at home. And so we have a positive times a negative gives us a negative bias. By removing that, our estimate becomes less negative or more positive. These are just a few of the variables that we could put into this regression. Estimating the wage gap is a very complex question that we've just started to scratch the surface on here. In the next video, we're going to move on to our last strategy for dealing with omitted variables, which is proxy variables.